Hi, everybody. I'm Brian Mao, and today I'm going to talk about WebRTC. So that's me, longtime Apple developer. So a little bit of introduction. I'm from LA. Originally, I was born and raised in the Bay Area, but I made my tech career here. I'm CTO of a startup called You and Me, which is basically FaceTime for pay using WebRTC. So let's just start off with a show of hands. How many of you have seen a WebRTC demo before? OK. How many of you have built something with WebRTC before? Can even be just like a demo. OK, cool. How many of you have something in production with WebRTC right now? Awesome, very cool. OK, so for people who didn't raise their hand at all, what is WebRTC? So first off, it's access to the camera, audio, mic, and screen. So just with this capability, you can do a lot of things. Secondly, it's peer-to-peer communication in the browser. So a browser can actually connect with another browser without a central server, and they can stream media and data to each other. Third, it's techniques for traversing NAT. So a lot of devices don't have their own public IP. They sit behind a router, they sit behind a firewall, and WebRTC provides methods for traversing to get to people behind a router. Fourth, it's high-quality, royalty-free codecs. So streaming media used to be proprietary. It used to be closed. It used to be expensive. But now, it's interoperable, it's open, and it's free. And lastly, it's a data channel. So a lot of these presentations, if you see WebRTC presentations, they talk about data as like a other, right? Like they talk about the camera, the microphone, and data. Like they don't know what you can do with that last piece of information. But we're going to look at some of the things we can do with that. So what are the use cases for WebRTC? Well, the main drivers are VoIP and video chat. Those are the two initiatives that caused WebRTC to come into existence. But developers that don't have this as a background have come up with really interesting things like multiplayer gaming. It's a demo called Banana Bread. They've come up with screen capture software where you can record like we're recording. Instant messaging. Peer CDN, as mentioned. Basically, a website hosts the files and distributes them to peers rather than a server hosting it. The browser can host and share. WebTorrent is the next extension of that, where it's a completely in-browser, peer-to-peer streaming platform that does BitTorrenting right in the browser. Music visualization. Some of you recognize this guy. He did a demo a couple months ago where he visualized music coming from his browser. IoT interconnectivity. Security cameras with like face detection and stuff like that. Telepresence robots. This is the guy that shows up to work when you're sick, and he beams a video right there. Who knows what else we'll come up with? What types of things are better if they're faster, more private, and more decentralized? OK. Earth to computer. All right. RTC, what does real-time even mean? So when we talk about real-time communications, what we're really talking about is we want the fastest stuff. We want UDP connections, not AJAX or TCP/IP, because UDP is relatively much faster than TCP/IP. We want video and audio streaming, and we want it to be peer-to-peer, because going directly from browser to browser skips any sort of intermediate servers, which slow down the connection. So we're going to look here at a naive example. Don't worry, if this is too small, we're going to dive in. Basically, this is inspired by Wes Boss. He did a security camera example, but I added my own sort of layer of dumbness to make a point here. So we'll take a look at that. So we'll start with broadcast. And these elements here is video, canvas, and context. Those are not WebRTC. Those are things we know about. Those are just how we display video. here's your first piece of WebRTC. It's called media constraints. And basically, this is an object that tells us what type of media we're going to grab. So sometimes we look at this, I should say, it can be simple or it can be complex. And you can get very specific with your media constraints. But in my experience, it's better to keep this simple because what happens is you get a false negative, right? You ask for something really specific and the browser says, I don't have that. But you do have it. You have a camera and the camera would have been good enough. So in my case, I'm just going to use video equals true because I want to guarantee that I get a camera back. All right, so next up, I'm going to pass the media constraints into getUserMedia. Basically, getUserMedia is a function that gets the user media, right? So basically, if you have used WebRTC in the past, you're used to the callback version of it. Basically, getUserMedia, it used to be made out of callbacks, but now it's promise-based. There's a lot of shims in browsers and things that make the old one point to the new one. So if you write the old one out, you may get pointed to the new one if you're using the shim. But the old one, the bottom one, is going away. So going forward, using promises is your safest bet. OK, I'll talk a little bit about media streams. Basically, streams are composed of tracks. And tracks can contain any number of audio or video. So they can be one video track and one audio track, or one video track and 7 audio tracks, one video track and no audio tracks, no video and no audio tracks, which is a bad situation, but it can happen. And then there's something called source object, which basically video has a source attribute, which we're all familiar with using. But then there's also source object, which is we take the stream and we directly apply it to the video tag. OK, I'm going to walk from getting my camera into the canvas. I'm going to start with my stream. I'm going to change my canvas width and height to match the video width and height. I'm going to draw the video to the canvas. I'm going to take a snapshot of that canvas. And then I'm going to socket.io emit that image. And I'm going to do it 10 times a second. And that's going to make my video. And on the other client, what I'm going to do is I'm going to listen for emitted images, and I'm going to display them on the image tag. That sounds crazy, right? Let's see if that works. Oh, God, dear God, please work. You know what? I forgot my phone. No, it's up here. Sorry about that, everybody. Hang in there, hang tight. Here we go.
Not a live demo.
This is right. 777. Right, if it's not, yeah, exactly. Too good to be true, right? All right. Hey. Wow. Woo. So that's a little bit cool. I mean, we were emitting images up to socket.io, and we got the camera. And with Canvas, we can do some kind of fun things, like we can detect motion. We can run algorithms to detect the face. We can color the bits. We can add funny nose and glasses, Snapchat type stuff. But I have a feeling there was a better way, right? Thank God that worked, right? Phew, I was worried. But what if I told you there was a better way, right? What if instead of emitting image to socket.io, what if I could actually just take that stream and just send it to the other browser and skip socket.io? Introducing RTCPeerConnection. This is the JavaScript interface that represents a connection between a browser and another browser. It's actually a lot simpler than people realize, and it's a lot more available than people realize, and it's a lot more powerful than people realize. So I'm going to walk the walk again, but this time I'm not only going to grab video, I'm going to grab audio. And I'm going to get my user media. Then I'm going to take that stream, and I'm going to add stream. That's a method on PeerConnection. And then I'm going to create an offer. What is create an offer? Create an offer creates SDP, And it's promise-based means it returns SDP. What is SDP? Thank you. SDP is short for Session Description Protocol, and basically it contains all the information about the computer and what types of media it's going to stream and what types of media it's capable of decoding. So not only what it's sending out, but what it could receive if it were to receive something. OK. And then set local description is basically the mutator of PeerConnection. So create offer creates an offer, set local description sets the description on the PeerConnection. So let's like promise chain these out and console log it and just see what we get. Whoa, that is a lot of information. It's like really super technical and it's way beyond what I would talk about in 20 minutes, so I'm not going to talk about it. But I'm going to say that if you go to WebRTC hacks, these guys have put together a thing where you can copy paste your SDP in there, and it'll line by line highlight exactly what it means, whether you accept H.264, whether you accept VP8, all sorts of cool information about your connection, that sort of thing. It's very interesting if you're into that sort of thing. But it's not important what's in there right now. What's important is that we get this SDP over to the Peer browser. How do we get the SDP over to the Peer browser? This is where signaling comes in. So signaling is the mechanism that you use to transport SDP. And what's interesting about signaling is it's not defined in the WebRTC spec what mechanism you use. All that's defined is that you use a mechanism. They want you to be creative. They want you to think outside the box. Possible methods include SIP over WebSockets, XMPP Jabber message, Facebook message. You could email it. You could mail it in a letter. You could send it by carrier pigeon. It really doesn't matter, right? So what am I going to do to send this? Well, I have socket.io left over from my last project, so I'm just going to repurpose it here to send SDP. How cool is that? All right. People stop here and they say, "What? I thought WebRTC was peer-to-peer, and this is not peer-to-peer. This is sending." Okay, the media stream is peer-to-peer. How you distribute your SDP is not defined by WebRTC. You go ahead.
So one early negative of WebRTC I remember is that you couldn't control the bit rate, right, of how much you're sending over. Like if I'm like a video game would stream at 4K,
yes,
right, but that would mean if I was using RTC, the receivers would have to receive 4K, which would destroy a lot of computers, right? So does this solve that problem?
Part of the SDP is the bit rate. So what you can do is, if you want, you can parse the bit rate, or you can parse the SDP, replace it, and this is what I do in my application, is I actually parse the SDP and replace 4K with like 512 or some more reasonable, sane number, especially since my application is mobile primarily. So yes, that's a very good point. You can parse the SDP, but if you don't, it will just rate adjust all the way up to like 1080p video. Yeah. If you have two people who are capable of doing 1080p video, it will absolutely do that. WebRTC does not actually specify in it what types of signaling method you use, but it does actually, it uses the word novel to say that you can come up with any method you want. Like if you are a big decentralized web guy, you could find a way to put it on the blockchain. You could find a way to distribute it as a localhost file. You could come up with ways of decentralizing SDP distribution. If you are a VoIP person and you like, if you like acronyms, you can do SIP, which is a common and prescribed way to do it. But since I have like 20 minutes to deliver this thing, I'm going to use socket.io. So we're going to look now at the Peer browser, right? So we talked about what browser A is doing to create an offer. And now we're going to look at browser B and what it does to receive an offer. So it sets up a socket to listen for offers. When it receives an offer, it sets remote description, which is basically the companion to set local description. But it basically is a companion to set local description. And then create answer is basically the companion to create offer, but it also includes the SDP that was in the offer. So create answer is the offer plus the answer. And then what we're going to do is we're going to set local description on browser B's peer connection. And then we're going to socket emit that local description as an answer back to browser A. Oh, and we are going to on add stream, because pretty soon we're going to start receiving a stream. We are going to add that stream to the video object. All right, so back to browser A. And socket on answer, we are going to set remote description with the message that we received. And as soon as that happens, video should start happening. Oh, here we go. All right, hold your horses, right? Wish me luck. All right, here we go. Allow. Hey. Ta-da, we are streaming. And what's crazy about what we're doing right here is this is not Socket.io. It was Socket.io to distribute the SDP. But this browser is talking directly to this browser with no server. There is no server in here. These two people are just peer-to-peer communicating.
So once it's figured out the most common public IP.
Oh, okay. All right, cool. Amazing. All right, so the next slide says, did that work? And it looks like it worked. All right. Oh, try it again. That's not the slide. I see the slide, but you guys don't see the slide. All right, did that work? Thank you, thank you. All right, so bonus round. Let's talk about WebRTC in the wild. A lot of devices don't have public IP addresses, right? They're behind a router, they're behind firewalls, they're behind Starbucks Wi-Fi, they're behind places where it can't just totally peer-to-peer. So in that case, let's look at some systems that we can use to get through routers. Stun is a common one, and what Stun does is it basically is a public server that exists out on the internet that a browser behind a firewall will say, what address, what port am I? And when it responds back with, oh, your port 1234, your address 789, right? I say, great, hold the door open, and I'm going to distribute that address to my peers. And they're all going to come in and say, OK, party time. We're all going to come in here, and we're going to peer your video stream off of this open port that the Sun server opened for us. Let's take a look at that configuration. So Google is one Stun provider. I've rolled my own Stun server. Basically, Stun servers are low resources, and they're cheap to operate. So people don't do anything to secure them. And they're out there for the public good. However, if you're on a symmetric routing environment, that doesn't necessarily work. So we create another thing called turn, which turn is Stun with also a media relay component. So in this case, I ask, oh, what's my IP address? And it tells me and say, great, my peers are all going to pick up my video at your server. So that's the way, that's like the total fallback case for if you're in a situation of extreme firewalling, you can still fall back to a turn server. Turn servers are expensive. They're not free. They're expensive to host. And let's take a look at what a turn server configuration looks like. OK, there's my password in plain text on the browser. Don't use long-term passwords. Don't use your password from 1998. Don't use your long-term passwords. Consider rotating them every few minutes, because otherwise everyone can use my expensive turn server. OK, so one more acronym. ICE candidates. ICE candidates are the string descriptors of what you receive from the turn or stun service. So it says, you know, your port 123. OK, I distribute ICE candidates to my peers. These acronyms are terrible, and every time I look them up, they never said the same thing. It's like session traversal, session utilities. It's never the same thing twice. These are the worst acronyms ever. Somebody is being paid to make this more complicated than it really is. Let's take a look at how easy this is in real life. Okay, so before I had RTCPeerConnection constructor with an empty parameters. This time I'm going to pass RTC configuration as a config, as a parameter of my constructor. Then I'm going to add an ICE candidate listener. And if the listener picks up an ICE candidate, it's going to distribute that ICE candidate to my peers. And my peers are also gathering ICE candidates. So when they receive a candidate, they are going to put it on their PeerConnection object, and I'm going to put it on my PeerConnection object. And the moment we both have each other's and our own PeerConnections, we're connecting. We're connecting through firewalls. This is easy. This is actually less lines of code than there are acronyms. Honestly, like once you get past those difficult terminologies, this is very, very, very powerful. So enough with the tech talk. Can I use this? Safari 11 now supports WebRTC. They released that this month. They were the last holdout, and now they support it, which means all the browsers support it. And you can imagine what type of chutzpah I have to do an entire presentation on WebRTC, including the video, completely on Safari, which was just released like days ago, right? The timing could not have been better. It's a huge empowerment win for browsers, right? The fact that browsers can just stream media to other browsers willing, that's super powerful. It's like a superpower for your browser. And it's like a superpower that we've had since like 2012 or something, but we barely knew it. It's right there, right in front of us, and it's in all the browsers. So what's interesting now is with all the browsers supporting it, and growing interest in decentralized things, it's time to start thinking about where this fits in your day-to-day tool belt and what types of things you guys can build with it. Okay, hopefully I've demystified some of that for you guys. Now, on the next slide, I have links to code and demos. And thank you guys so much, and I will be here for your questions. Thank you again.
All right, I think we can take a few questions real quick. We don't have a mic to pass around, so please use your big boy, big girl voice. And Brian, if you could, repeat the question to the microphone.
You got it.
We got one in the back.
What about security issues? In the first example, you were talking about using WebSocket, so we have HTTP handshake before that, so it can be secure. So you said that it can distribute HTTP in any kind of way. So there's got to be some way that someone can intercept it and take SDP and get whatever they want from the source that you're streaming.
Okay, to re-summarize, security. If the STP, if the STP is delivered over socket.io, who's to stop from many peers from picking up that same STP? It depends on the intent of your app. In this particular case, this demo was built so that any person who loads up that URL would have gotten the stream. So actually, if every single person pulled out their phone and went to that URL, they would all get the stream. If I were purpose building it, what I would do is I would use socket.io, and I would use this specific, socket.io creates specific unique IDs for each person connecting. And in my video chat demo here, I do in fact do that, where I specifically only send the SDP to the one person who's supposed to get it. Other things related to security, I'll kind of just round that out, which is that it's done in DTLS. The actual media streaming is actually done in DTLS, so it's actually like almost completely impossible to intercept that media stream if you are not the peer that it's intended for. It's actually very secure. There was a big concern with RTC with RTCPeerConnection that it leaked your true IP. And that was a truth in like 2013, 2014. And people who are afraid of it still to this day disable it from their browser, but it is not a truth today. It does not leak your public IP address. If you are someone who's trying to, like, for instance, watch Hulu videos in a country, pretend you're in another country or whatever. So it's good for people that still want to mask their identity in that way.
I have a question. Is WebRTC smart enough to use LAN if both devices run the same Wi-Fi?
Yes, it absolutely. So the ICE connection candidates that come up, if you don't do any ICE connection, the only two candidates that come back in your SDP are same LAN. And the video stream that you were in fact watching right there was same LAN, which is why it's very good bit rate.
How are you doing it on iOS today, and what about iOS in the future?
So 2 answers. The Safari 11 that was just released in the last 5 days or whatever fully supports this. So that was just regular, no plugins, no nothing, just regular Safari 11 WebRTC. My primary day job is to write an app. I don't actually even do JavaScript in the day. What I do is I write Objective-C in Swift. And in that case, in a native app, it's a compiled plugin that Google provides. And actually, there's 2 sort of competing ones. There's one that Ericsson did, and there's one that Google did that both implement the same standard, one with VP8 and one with H.264. That you can use that in your binary if you're going to do an app. It's my hope that someday I'll give this talk again to the crowd at Swift Coders, because they are not as familiar with WebRTC as a concept. I think they would have their minds blown even more.
What about the future?
So right now it's 1.0, and they're migrating toward a 1.1 spec. The 1.0 is in request for comments portion of working draft. And right now, WebRTC, the Safari, the way they implement WebRTC is they have old fallbacks under a flag, and if you don't turn on that flag, it only works with the newest spec. And it only turns on the older spec if you turn on that flag. So these samples that I gave you are all up to date for now.
Very cool. All right. Thank you very much, Ryan.
Thank you. Thank you. Yes.